Welcome to MECH 2020 Statics and Dynamics Tutorial 3. Today we will be continuing moment discussion as well as doing more practice problems with moment. In this tutorial we will cover the principle of transmissibility, moment couples, and various moment examples. You may ask why much of the section is devoted to examples. Well, in statics, learning and understanding the material is primarily from doing a lot of examples and learning how to approach a variety of problems with a few simple methods and formulas. The principle of transmissibility is a bit of a complex subject, so we've split the topics into its force and moment definitions. For forces, the principle of transmissibility states that all forces of a given magnitude and line of action, so that the forces are not only parallel but also collinear, will achieve the same translational motion and require the same force to reach an equilibrium state. In the systems with F and F prime shown in the diagram below, both systems will have the same resultant force and require the same opposition force, this opposition force for example, to achieve an equilibrium state. In a real-world example, a dragging force and a pushing force in the box, so long as they act in the same direction, will cause the same resultant movement on the box. And when I mean same direction, I mean same vector direction. For moment, the principle of transmissibility states that a force on the same line of action and with the same magnitude as another force will have the same moment about any given point of measurement. Recall from geometry that a plane may be defined by the combination of a point and a line. In the diagram shown here, wherever the force vector is positioned on the same line of action yields the same moment magnitude due to the magnitude being equal to Fr sine theta. The moment axis is also the same due to the force vector being on the same line and the moment point being static. Since they are both static, or they are on the same line of action and the moment point is static, they form the same plane and plane normal vector as both moments share a point and the line, and it's actually equal directly to the perpendicular distance radius and the force vector magnitude. Here we have another example. The point of application of the force does not matter for the moment calculation so long as it is on the same line of action. This is akin to the box example that I mentioned in slide 3. Now let's do a moment problem with the principle of transmissibility. Please pause the video and take 5 minutes to attempt this problem yourself. Now that you have attempted this problem yourself, let's go over our approach. First, we'll evaluate the moment based on physical connections. We break the diagram into a graphical positioning of vectors, as shown here. We find the length of the wire shown, use it to create a unit vector in the direction of the wire shown, and perform scalar multiplication of the tension magnitude and the wire unit vector to create the tension force vector, as seen here. In our graphical representation, the radius vector is just pointed in the positive x-axis direction. From here, we form our moment determinant and get our moment axis vector as shown here. Next, we will use the principle of transmissibility to evaluate the moment from the point on the wall. The calculation of the force vector remains the same as the previous problem part. However, the radius vector is taken from the point on the wall, whereas it was normally from here, it is now, let me switch color for this, from here, forming a vector of 2.4j plus negative 4k. We evaluate the determinant to get the same resultant moment axis as the previous part, thus demonstrating the effect of the principle of transmissibility. Next, we will be covering moment couples. A moment couple is a system with no net force, but has a net moment. the object in the physical world would rotate or spin in place. Here we see the mathematical foundation for a moment couple. The object has no net force, therefore there is no translational movement of the center. However, since the moment components of the forces are turning the object in the same clockwise direction, as we can see here, and some arrows for clarity, the moment is non-zero for this object. Here we have a problem on moment coupling. Please pause the video and take a few minutes to attempt this problem yourself. Now that you have attempted this problem yourself, we'll go over our approach. We find the length AE and divide the vector components of AE with the length to get the unit vector of AE. We then multiply this with the tension force magnitude to get the tension vector from point A, which is shown here. We then construct the radius vector from O to A and find the cross product of the radius and force vectors. This yields us the moment of the tension from A about point O. Since the force in cable AE is a tensile force, the force at E points away from E, just how the force at A points away from A. Thus, the force at point E is the same as the negative of the force at point A, placed at E. We then construct the radius vector from O to E and find the cross product of the radius and force vectors. This yields us the moment of the tension from E about the point O. Here we have another problem on moment. Please pause the video and take 5 minutes to attempt this problem yourself. Now that you have attempted this problem yourself, we'll go over our approach. We find the length of cable CA and turn the distance vector of CA into a unit vector. Then we multiply this unit vector onto the magnitude for the tension force vector CA. We construct the radius vector from the origin O to the point C, over here, and perform the moment cross product operation to find the general moment axis vector, which is here. We perform dot product multiplication, not shown here, with the vector form of each coordinate axis and the general moment axis to find the moment of the force vector CA about each coordinate axis. Although this step seems no different from separating the components and calling those the components along the axes, it will be important when handling more complex moment axes. Examples should not take shortcuts. Here we get our answer. Here we have another problem on moment. Please pause the video and take a few minutes to attempt this problem yourself. Now that you have attempted this problem yourself, we'll go over our approach. We find the length AE and divide the components of AE with it to get the unit vector of AE. We then multiply this with the tension force magnitude to get the tension vector point from A. We then construct the radius vector from D to B and find the cross product of the radius and force vectors. Then we must find the unit vector of the direction vector dB. Why do we do this step? We do this step so that we must make sure that the moment axis is taken in such a way that the results are not inflated, yet still accurately reflect the angle between the general moment axis and modified moment axis. If we recall the dot product formula of magnitude V1 times magnitude V2 times cosine theta, we see that to find the projection of the moment vector onto the modified axis vector, we need the unit vector of the modified axis. We perform the cross product operation with the radius and force vectors, then perform an additional dot product operation on the general moment axis with the unit vector of dB. Thus, we arrive at our answer here, which is the moment about dB. Let's combine the force and moment couples together now. Please pause the video and take a few minutes to attempt this problem yourself. Now that you have attempted this problem yourself, we'll go over our approach. We first sum the forces of the entire system to get a net force vector in all 3 dimensions. This is simplified since all of the forces are on the coordinate axes. We then find the moments of each of these forces about the point C and sum them. The combination of the resultant force and the resultant moment form the force couple system about the point C. This marks the end of tutorial 3 of MECH 2020 Statics and Dynamics. The topic of the next tutorial will be rigid body equilibrium. If you have any additional questions on the content featured here, you may email your course professor or tutorial instructor. Until then, goodbye.